Okay, so what we're going to start discussing is the Lebesgue integral finally. And right, so the basic foundation for the Lebesgue integral is going to be what we ended off with last time, which was a reformulation of the Riemann integral in terms of step functions. So let me recall what we did. So last time, we basically proved that, the modified lower Lebesgue integral is given by this supremum here. This is for homework. So that f is Riemann integrable on A to B if these two are going to be equal. And if they are equal, we say that is the Lebesgue integral of f over A to B. So we're going to basically do the same thing for the Lebesgue integral. We're going to, well, an interval A to B is going to be replaced initially by a measurable set that has finite measure. And f is going to be a measurable function on this measurable set. And we're going to find the lower and the upper Lebesgue integrals in exactly the same way. It's going to be the integral. We're going to basically take the supremum of the integral of 5x dx over e, where instead of phi being a step function, we're going to take the supremum over all integrals of simple functions. Okay. Where still the simple function phi will be less than or equal to f here, and psi will be bigger or equal to f here. Okay. So in that sense, yeah, all we're doing in defining the Lebesgue integral is replacing step function with simple function. Okay, so we're going to say f is Lebesgue integrable if the lower and upper Lebesgue integral coincide. And if they coincide, that common number is going to be the Lebesgue integral of my measurable function. Okay, so before we go down that path, we need to discuss integrating, defining the Lebesgue integral of a simple function. So let's do that right now. Okay, so for motivation, remember what we proved last time, that if I have a step function, so that this is constant on each partition interval, the open partition interval, corresponding to some partition of A to B. So we proved last time that the Riemann integral, should be an R here, but that's all right. The Riemann integral, as it better be, is essentially the sum of all these red areas here. Okay? So this is the height of my step function on my interval, and the interval is, well, this is just the width of the interval. Okay? So when n equals 3, this literally is, the sum here is the sum of the red areas here. You know, the sum of the 3 red area under the rectangles. Okay? So this fact here essentially tells us how to define the Lebesgue integral for a simple function. Okay. Yeah, as I said a moment ago, the idea of the Lebesgue integral, I should mention this is what our book is doing. The idea of, you know, for the Lebesgue integral is just, a moment. Yeah, is to just replace step functions with simple functions in here, essentially. Okay, right, so let's say we have a measurable set. We're going to start off assuming, as I mentioned, that E is has finite Lebesgue measure. So let's say phi is a simple function, so it's measurable, and it has a finite range, meaning it takes on a finite number of values. Let's say you know, the range, the direct image of E under phi is A1, A2 through AN. We're assuming these are distinct real numbers. Okay? So if we define EJ to be the inverse image of each of the singletons, so EJ is just a set of all x in E where 5x is AJ. Then we have 5x is AJ for x and EJ. By literally the definition I just said a second ago. Okay. Because this is the the range of E, it's the direct image of E under phi. E is this union, and it's a disjoint union because we're assuming these are distinct real numbers. And we can write phi of x as this sum here. This is what we call the canonical decomposition of our of our simple function. Okay, so I'm going to define the Lebesgue integral of 5x over E just to be this sum here. Okay, and you can actually check, I encourage you to check it, that this actually extends the definition, or not the definition, but the result we just mentioned a second ago for taking the Riemann integral of a step function. Okay. Because, well, so when I write this here, I'm omitting, well, basically the terms corresponding to, phi of x on these endpoints, where phi of x on the endpoints is not what phi of x is on any of my open intervals. But phi of x being this one here, let's say, and this one here, phi of x is this y value at x0. The singleton x0 has measure 0. Singleton x2 has measure 0. So there's no contribution to the sum here. If any of the EJs is a singleton. Okay? So that basically essentially proves that this definition here coincides with the integral of a step function. And by that I mean, or I'm implicitly reminding you and telling you that step functions are simple functions. Trivially, a step function only takes on finitely many values, and you can check trivially that step function is measurable. So yeah, so we have a definition of integrating the Lebesgue integral of a simple function that extends, coincides with the Riemann integral of a step function on a closed interval. All right, so it's important to prove the following. It's a technical thing we have to prove, but we still have to prove it. So let's say I can write phi of x as this sum here, where the AIs are disjoint. They're all subsets of E, and assume they're measurable. If I can do that, then this integral is going to be this sum here. So I want to make an important point. This looks obvious, looks like the definition, but it's not, because there could be repeats here. And the union of the AIs is not necessarily E. If there are no repeats and the union of the AIs is E, then you can prove, and I encourage you to do that, that this is going to be the canonical decomposition of my simple function. Okay? But there can be repeats, and the union of the AIs need not be E, so this result does not follow from definition. It needs to be proved. And I also want to make clear that you might be saying, well, hey, wait a minute, isn't the integral of a sum the sum of an integral, and can't you pull out constants? Well, you can basically trivially prove that, yeah, when you're integrating simple functions, you can prove it. You can pull out constants, but it is not trivial at all to prove that the sum, the integral of two simple functions is the sum, integral of the sum of two simple functions. It's not easy to prove that the integral of a sum is a sum of the integral for simple functions. And actually, we're going to need this proposition to prove that. We're going to need this proposition to prove that integrating simple functions is linear. All right, so how do I prove this? Well, so first I want a reduction. So let's assume E is not this disjoint union. Okay. In that case, let's set big A m plus 1 to be E. Take away this union. So clearly, E is going to be the disjoint union of the AIs from I equals 1 to n plus 1. Because everything is a subset of, the union is a subset of E, because all the AIs are a subset of E. So either, let's say X is in E, either X is in this union, or it's not in this union. If it's in this union, well, it's in one of the AIs for I equals 1 to m. It's not in the union. It's by definition in AM plus 1. Okay. And 5x is going to be given by the sum here, which is absolutely trivial because this really is just the sum I equals 1 to m, lambda I, characteristic function AI of x, because lambda 0 is 0. Sorry, lambda m plus 1 is 0. So I'm just kind of doing something silly and including the, that 0 term in the sum. Okay. So let's assume we have proved this proposition under the assumption that the disjoint union of the AIs is E. Okay. Then if that is true, then this integral will be given by this sum here. But again, lambda m plus 1 is 0. And everything is a subset of E. E has finite measure. So the measure of everything is finite. So there's no funny business of how do we deal with 0 times infinity. The m plus 1 term is 0. So if we can prove the proposition under this assumption, then we have in general proved the proposition. Okay. Because we just started off with 5x and these AIs. And we've proven, assuming what's in the box is true, that this integral is exactly the sum we wanted to prove it is. So without loss of generality, we're going to assume that the disjoint union of the AIs is E. Okay, so let's write phi. Let's write the canonical decomposition of phi. Okay, so remember again, what does that mean? Just go back here. That means that we're writing 5x to be this sum here, where EJ is the inverse image of the AJs. Okay. So 5x is AJ for x and J. Okay. Okay. Right. So 5x is AJ on EJ. On the other hand, 5x is lambda I on AI. Just by definition, these are if x is in AI and none of these other sets. Well, if x is in AI, it can't be in any of these other sets because these are pairwise disjoint. And if x is in AI, then 5x is just lambda I because characteristic function of, AI plug in x is 1, if x is an AI. Okay, so 5x is equal to lambda I on big AI. Well, this is, remember, the image of E under phi. Okay, so these are exactly the values that phi takes on. Lambda I is one of these values that phi takes on. Remember, there could be repeats here. Okay? But all this is saying is that lambda I has to be one of these. So for each I from 1 to m, lambda I has to be one of these. Okay? And that also means AI is going to be a subset of EJ. For x in AI, 5x is lambda I is AJ. So that means x is, if x is in AI, big AI, it's in the inverse image of, well, little aj. So it's in big EJ. So if x is in big AI, it's in big EJ. Okay. So let's define ij to be the set of all I from 1 to m, where lambda I is equal to aj. Okay. So I claim that these sets are pairwise disjoint. That's fairly obvious because, remember, we're assuming that these are distinct here. A1 through AN are, little a1 through AN are distinct. We're writing the image of E under phi as this distinct set of finite set of numbers. So if there is something common to ij and ij prime, for j not equal to j prime, then by definition aj is lambda I, and aj prime is lambda I, just by this definition here, so that these are not distinct, even though j is not j prime. So that's impossible. So if j is not equal to j prime, then big ij is, has nothing in common with big ij prime. These sets are pairwise disjoint. Okay. So further, we have this equality right here, and this is pretty trivial. We just proved that this is a disjoint union. These are pairwise disjoint. Okay. Clearly, this union is a subset of 1 through m, the integers 1 through m, because each ij is a subset of the integers 1 through m. On the other hand, this is a subset of this union because if I is something from 1 through m, I is in big ij for some j. That's exactly what we just had here. So for each I, lambda I is one of the aj's, so I is in big ij. Lambda I is aj. Okay. So every I from 1 to m is in one of these big ij's. And homework, and this is where you're going to use the fact that E is the disjoint union of the AIs, what we are assuming right here. So homework is going to be that also each EJ can be written as this disjoint union. Okay. So if this is true, then, well, remember the assumption is that the AIs are measurable. They're disjoint. So using finite additivity, we have that the measure of EJ is going to be the sum of this measure. So let's put this to good use. Okay. So remember, the definition of this integral is going to be the sum here, where sum j equals 1 to n, aj, characteristic function of ej, is the canonical decomposition of my simple function. Okay. So I can plug this in. I have an MEJ here. I can plug this in. Let's do that. Sorry, let's go back here. Okay, so I plugged MEJ is going to be the sum. Plug that in here. All I'm going to do is trivially bring in the AJ into the sum here. Well, remember, if little I is in big IJ, then lambda I is AJ. So by definition, lambda I, AJ is lambda I if little I is in big IJ. Just go back and look at the definition. Okay. But this is going to be just a sum I equals 1 to m, because I said that the set of all natural numbers from 1 to m is going to be the disjoint union of these ij's. Okay? So there's no repeats when we take this sum here. There's no repeats. We get exactly I equals 1 to m. Every I is counted and counted only once. Just check that if you're unsure of that. And that, again, just follows from the fact that this is a disjoint union right here. And that's exactly what we wanted to prove. We wanted to prove that the integral is given by this sum here, lambda I m a I. So we go back. This is exactly what we wanted to prove. Okay. And of course, remember, we're proving this under the assumption that the union of the AIs, big AIs, is E, which, as I mentioned, allows you to do the homework, which is that EJ is going to be this sum. Okay, so let's see now how this technical annoying result allows us to prove linearity of integration of simple functions. So, right, let's say E is finite measure. I have two simple functions. So I claim that the integral of the sum is the sum of the integral, and by induction, this holds for finite sum of any linear combination of simple functions. I should mention clearly a linear combination of simple functions is simple, it's measurable because all the functions are measurable, and because each function in the sum takes on finitely many values, so does the sum itself. And two, we actually need one to prove this. Two is that if we have two simple functions, one big or equal to the other on E, I should mention E is measurable, of course, then the Lebesgue integral on simple functions is monotone in this sense. Okay. So what's the proof? Like I said, the proof is not trivial at all. If I literally gave it for homework, you would probably just try to use the definition to prove it and get completely lost. But anyway. All right, so let's write 5x. Let's do the canonical decomposition of 5x. All right, so, well, let's take care of the very easy case. So that means alpha 5x, alpha and beta are real numbers. Well, just bring this inside. You can either check that this will be the canonical decomposition of alpha 5x if this is the canonical decomposition of 5x. Or you can just use the fact that, well, since this is the canonical decomposition, the EIs are disjoint, and we're writing alpha 5x as the sum here where the EIs are disjoint. So by definition, alpha integral of 5x dx is going to be this sum here. And just pull the alpha inside. And, well, this is going to be equal to either, again, by definition, or using the fact that this is actually a canonical decomposition for alpha 5x. Yeah, so that's basically true. There's really nothing to prove here. So this means that I can assume alpha is beta is 1 when I prove this. If I can prove it in the case alpha is beta is 1, I can just basically apply this fact here that I can pull out constants to just looking at the simple function alpha 5x plus the simple function beta psi of x. All right, so let's assume that, a little too far, a little ahead of myself. Let's assume alpha is beta is 1. Okay, so now let's write the canonical decomposition of psi. Okay. So j equals 1 to m, aj prime, characteristic function of ej prime x. Because we're writing these functions in terms of the in terms of the canonical decomposition, as I mentioned, E is going to be the disjoint union of the EIs, and it's the disjoint union of the EJ primes. Okay. So that means I can write EJ prime as this disjoint union. Okay. Just essentially use this fact here and intersect both sides with EJ prime. And if I want to use this fact here and intersect both sides with EI, I get that EI is going to be this disjoint union. Okay. And of course, because this is, we're writing the canonical decomposition of my simple functions, all these sets, the EIs and the EJ primes, are a subset of E. Okay, so what this means is that we have the following decomposition of characteristic functions. That's just trivial from the definition of characteristic function, and the fact that these are disjoint unions. So we're going to plug this in. So plugging this fact in, so I'm literally plugging this here into this, and I'm going to plug this here into this here. So when I do that, I get the following sums here. All right. So, so when I write this here, I'm really thinking of, one summation I equals 1 to n, j equals 1 to n. You can write that obviously as one summation. And same thing here. I'm really thinking of this as just one summation. And I'm interchanging the order of summation here because, well, finite sum, it's not really doing anything. Okay. So when I think of this as one summation, I most definitely have repeats. I definitely am going to have, well, probably, I shouldn't say definitely, but, in general, you're definitely going to have repeats because we have the same aj prime for each I equals 1 to n. We have the same ai for j equals 1 to m. So there in general is going to be repeats, but it doesn't matter because the EI intersect EJs, all these sets are disjoint. So I can use that proposition that I just proved. So because these are pairwise disjoint, and because if I just add these two functions up, I just add them up like I would add any two functions up, simple function or not. So I can use the previous proposition here, where here I still might have repeats. I might have repeats in the sum here for the AI plus AJ primes. There's no reason why we don't have it. But these are pairwise disjoint. So the previous proposition says I know how to integrate this, and it's just this sum here. Now all I'm going to do is break this up into two sums and use the proposition one more time. Okay. This integral here is going to be this sum. This integral here is going to be this sum. And again, I, in general, will have repeats because for each j, I have the same AI. For each I have the same AJ prime. That's okay. The characters, the sets here, EI intersect EJ prime, they are disjoint. They're pairwise disjoint. So the previous proposition says that from these two facts here, I can integrate 5x, I can integrate psi of x, and the integral is going to be respectively, this is the integral of 5x, this is the integral of psi of x. And that's exactly what we wanted to prove, that the integral of the sum is the sum of this integral. Okay? So yeah, it took a lot of work to prove linearity, but what that practically means is that, well, it's just less work in the future. That's basically what the point of this whole video is. We put in some work in this video. It's going to pay off when we talk about the Lebesgue integral for more general functions other than simple functions. Okay, so let's prove 2. So, right. So this integral here is bigger or equal to this integral. Is the same thing as saying, well, just subtract this number here. Again, this is finite. There's no issue with that. The Lebesgue integral of a simple function is always finite because we're assuming E has finite measure. So this is true trivially if and only if this is true. Just bring this to the right-hand side. We know that this sum here is going to be the integral of the sum is the sum of this integral. Basically same thing. The integral, the difference of an integral is the integral of the difference. Okay. So this is true if and only if this is true based on 1. But this is a simple function. It takes on finitely many values. It's measurable because we have 2 real valued measurable functions on E. And it's absolutely trivial by definition that if this is non-negative, and we're assuming this is non-negative on all of E, that's our assumption. Let's go back. We're assuming psi is bigger or equal to phi on E. So psi minus phi on E is a non-negative function. It's a non-negative simple function, and it's absolutely trivial that when you integrate a non-negative simple function, you get something non-negative. And that's just by definition. Why do I say that? Because, well, if I have a non-negative function, then all these are non-negative. Lebesgue measure is always non-negative. So you're summing up something non-negative times something non-negative, you get something non-negative. Okay. So if I integrate a non-negative simple function, that's always non-negative. So that finishes the proof. This integral here is non-negative because by assumption, this is a non-negative simple function. All right, so yeah, we'll end there, and the next video is going to be essentially what I start off with, and actually just defining the Lebesgue integral for basically an arbitrary function. Not exactly arbitrary. Like the Riemann integral, we need to assume, well, one, we're dealing with a set of finite measure. You only do the Riemann integral with, you only do the Riemann integral over a closed interval. And two, we're going to assume f is bounded. Right? We'll have to, take it a step further later to define the Lebesgue integral over a set of infinite measure, and f is unbounded, but we'll do that maybe next week. All right, well, so long, stay healthy, and yeah, stay healthy, and I will hopefully see you guys sometime again. Bye-bye.